Hello, welcome back. So we are here on the next section of this chapter that's devoted to the wave equation. And today in this screencast, I'm going to talk to you about the separation of the wave equation. Well, I will explain to you what separation means in this case. Separation means that we are going to separate the position and the time variable. Okay, so let's do this. Just as a reminder, so far we were able to derive this wave equation in one dimension, and we found that it was actually a pretty simple and elegant form where we have second derivatives of the wave function with respect to time and with respect to position. These are connected through this equation, and we found the v is the velocity of the wave, and we discussed this in detail in details in the previous screencast. So now we are going to explore this equation a little bit more. I would like to also notice that maybe it's a good idea to make a mental copy of this equation in your head, since is going to stay with us for the entire screencast today. So let's get started. When we were looking for solution to that equation, we always wrote the wave function this way, where we separated the position and the time. So we were looking actually for harmonic solutions. When we meant by harmonic, we meant that's oscillatory solution. And we see that very well when we look at the real part of the equation. We find that we have a cosine omega t. So it's really a harmonic solution at a given frequency. So we solved this, and if we insert this equation directly in the wave equations for the previous slide, we obtain this equation here. And of course, since we assume the function for the time part of the function as to be e to the power I omega t, we essentially solve the equation for time, and we end up with an equation that just depends on the position. So that equation here that I have, the last equation we have on this slide, only has a position dependence, because we took care of the time. So in general, actually, as we've seen, it's very important to remember that there are, to the wave equation, there are multiple possible frequency omegas that can be used as a solution to the equation. We saw that in lots of details in many examples that we have looked at so far. In fact, for the continuous string, we even found that the number of frequencies is infinite, but that's not really an issue. So now that means that in general, this one specific solution of the equation will have a specific frequency, and this is why we write it this way. This equation is essentially just to remind us that different frequencies are possible. In fact, because we are dealing with linear equations, as we have done completely for the entirety of this course, a linear system, a linear equation, means that the linear combination of different solutions is also a solution to the problem. I mean, it's very essential to see this. So we can formally write this way, that a general solution is a linear combination of all the different solutions. So this is the most general case. That means also that the solution is not necessarily going to be periodic, since we have different frequencies, right? So if we sum different frequencies, the solution is not necessarily periodic, but we can always decompose the full solution as a sum of periodic function. Well, for those who remember Fourier transform, this is exactly what Fourier transforms do. They separate, they provide a decomposition of a function as a sum of its frequencies. So this is really equivalent to a Fourier transform. So we see that the function is no longer periodic in time in general, but that's fine. There's not a problem at all. I mean, if you're not convinced, try to look at what would be the period of the function that's written on top of this slide, and you will see that since we are using different frequency omega r, the function is no longer periodic in time. Okay, very good. So let's go back to where we started from. We use a solution like this for a given frequency, And the frequency, if you remember, was obtained for the specific system. So far, we have mostly calculated omega r using the secular equation, or calculating the determinant to make sure all the equations were compatible, just as a reminder. Now, what we see in this equation, we actually already separated the variable x and t. So we do not have any function that are of x and t at the same time. We can separate the function. So in this screencast, we are going to focus on that in a little bit more detail. So in fact, we can write in all generality, if we separate the variable x and t, we can write the wave function as the product of a function of position and a function of time that we wrote. The function of time we wrote chi of t. So now, if we go back to the wave equation, we can now substitute this type of solution into the equation, and we obtain an equation like this. Okay, we obtain an equation that's going to look like this. There's a lot of letters, a lot of symbols, but it's really a direct substitution within the wave equation, and we can rearrange things a little bit, and so that we have an equation that looks like this. So this equation, we can actually tell quite a bit just by looking at the shape of the equation. That's what we are going to do on the next slide. So what you can notice directly is that the left-hand side of this equation only depends on the position x. Likewise, the right-hand side only depends on the time. Therefore, we have two functions, one that depends on one parameter, and on one side that depends on the one parameter, and the other side that depends on another parameter. And obviously, because the two parameters are independent, we can, in order to solve this equation, both sides of the equation must be equal to a constant that does not depend on either time or position, right? This is a usual trick that we use, and what we are going to do in this case, we are going to suppose that that function, that particular constant that does not depend on position and time, we are going to write it minus omega square. Okay, we could write it anything we want, but we call it minus omega square simply because we are going to retrieve equations like we had before. But we do not make any assumption about what minus omega square is. It could be any number. It does not have to be negative, since omega can be a complex number. In fact, it's not going to be a complex number in our case, but it could be a complex number in all generalities. So now that we know that both the left-hand side and the right-hand side is equal to minus omega square, we can rewrite two equations, one for position and one for time. So for position, we obtain this equation. We just said that the left-hand side is equal to minus omega square, and we rearrange. And obviously, we know how to solve this. I would like also to attract your attention that I moved from partial derivative to normal derivative simply because the function psi is actually only dependent on one variable x, and we are going to do the same for chi with respect to time. We know the solution for this type of equation, right? The second derivative of function being proportional to the function itself. The only solutions are the exponential, the complex exponential, and we find this solution with the constant a and b. The constant a and b are going to be imposed by the boundary conditions, so conditions on the position. So likewise, we can do the same exercise on the time part of the equation, and we obtain this equation. And again, the equation is very much the same shape as we had before. The difference is now it's a function of time, and the solution looks the same as before, but now the constant c and d will be imposed by initial conditions that we have on the problem. So again, just so to make sure that we are keeping everything in check, we have two second order equations. So that means that we need four constants. So that are called boundary condition for position and initial condition for time. So it looks like everything is in good shape so far. So let's try to study this in a little bit more details. Now that we know solution for psi of x and chi of t, we know those two solutions, and then we can now look at the complete wave function as a function of x and time. So we are simply substituting in the solution, and what we find is that we are going to have a bunch of solution that will involve various arguments in the exponential, right? So we can write it this way, and I attract your attention that the fact that we have we use twice plus and minus, it means that we have 4 possibilities, and all the combinations are possible. In fact, if you want to write it explicitly, a general solution will be linear combination of those terms, with the weight of each term dependent on A, B, C, and D that I discussed before. So another thing that is good to remember is that you see that the argument is x plus vt or x minus vt, just like we advertised and discussed at length in the previous screencast. So it looks like we are in good shape. These are propagating waves, either to the left or to the right. To the right is x minus vt, and to the left is x plus vt. So everything is wonderful. Of course, let's not forget that different frequencies are possible. So specifically, just so you do not lose track of this, the solution can be dependent on a index r, for example, which will correspond to different frequencies. So by now, that shouldn't be a surprise to you, since we found so many solutions with different frequencies. So that's the typical terms that we will find look like this. And finally, the general solution will be a linear combination of those, and we will have something of this sort, with the coefficients A of r again will be determined by the kind of problem we're looking at. So what we have done so far is to simply look at the general shapes that we are talking about, and in fact we've done a great deal of work, because we have essentially solved the wave equation in one dimension in all generalities, and each of the specific problem we look at will correspond to the different coefficients that we have to determine. Again, we are not imposing ourselves, we are not imposing a periodic solution, because the sum of periodic functions is not a periodic function, unless the period is the same, of course, for all the functions that we sum. So we should feel pretty good about ourselves now, because we can really see that we have a complete solution to the problem. Now, we will see that the physics and the math is actually going to be very similar for each of the different phases that we have, so the different argument that we have. So we are going to focus now on, for example, this type of wave that I show here on this slide, which is a right-going wave of the type x minus vt. It's a good idea to not be stuck in the math so much. So let's try to see what we mean by phase. This is something I already mentioned a number of times, but maybe a little picture can be useful. You see that we have a complex exponential, and a complex exponential can be easily represented on the unitary circle, where we show the real part on the x-axis and the imaginary part on the y-axis. And basically what we are saying is that the wave function is proportional to this function here, which is somewhere on the unitary circle. And the phase, in other words, the angle that this vector makes with the real axis, is simply the phase that we have here. So this is the usual approach. It's a good idea to think about this, because it makes it very easy to perform sums, to understand what we mean by phase, what we understand by dephasing, and this kind of things. So this is really good. We see that the phase is changing with time, is changing with position, and so we have a really general solution. And again, just like I mentioned a few minutes ago, this particular solution is, in order to have a complete solution, you have to sum all the particular solution, and this particular solution again is one Fourier component of the wave function. So everything seems to be in good shape. Now, I know that we are going back and forth, and I'm sorry about this, but in order to make the notation a little bit cleaner, we are going to focus on this. So I dropped the r from omega, but you have to remember that different omegas are possible, and we will not forget that the general solution will involve different omegas. Okay. So let's try to examine this a little bit more, and this is what we are going to do until the end of this screencast. So for that, let's go back to the position-dependent equation. And we are going to try to study a little bit this term omega square over v square and what it actually means physically. And this is actually, this will allow me to introduce an extremely important concept of wave number. Again, there's no reason to, there's no difficulty here. It's just a matter of paying attention step by step. No mathematical difficulties, but a very important definition and also physical interpretation. So let's do this. It's just going to take me this slide to explain it to you. So usually people rewrite this equation this way, which is really no big deal. This is actually, this equation, this shape of equation is called the Helmholtz equation. And in order to get that equation, we simply said that k square is equal to omega square over v square. Again, this is a pure definition. But the thing is, k has a specific interpretation, which I'm going to do now. In fact, k is called the propagation constant. It's also called the wave number. So it's really the number of waves. So what do we mean by that when we talk about wave number? Well, the interpretation goes as follows. You know that the wavelength of this particular harmonic solution is going to be the distance for a complete vibration. Remember, here we are looking at one particular frequency. So this particular solution is periodic, and it has a wavelength lambda, and the wavelength lambda is going to be given by the number, the length between two equivalent points, or two maxima or two minima, whichever you want to pick. So the wavelength is going to be the velocity divided by the frequency. So if you look at, if I told you that the wavelength is the velocity of the wave times the times it takes, you would certainly understand that it's the wavelength. Well, the time it takes is the inverse of the frequency nu, so it's good. So it looks like we're in good shape. Now we have been using the angular frequency instead of the frequency itself. So the angular frequency is omega, and omega is just simply nu over 2 pi. So that's what we usually use, and we do that so that we don't have 2 pi's lying around everywhere in the exponential. Really, it's a more convention and makes notations easier. But in any case, the wavelength is 2 pi v over omega, and we see that v over omega is the inverse of k, according to the definition that I just provided. In other words, we find that k is equal to 2 pi over lambda. Just for a second, forget that we had a 2 pi here. K being equal to 1 over lambda simply means tell you how many waves we have per unit distance, right? If lambda is the length of the period, 1 over lambda is going to give you the number of such wave, complete wave, per unit distance. Here as I said before, we have the 2 pi, so really the wave number k is the total number of waves per unit distance times 2 pi, or in other words, per 2 pi distance, if you will. So k is really important because it gives you the wave number, which is simply related to how many wavelengths you have in a given period, in a given length. So you expect k to be very important because it's going to tell you how much oscillation you have in space, and of course give you a lot of information. So that's very useful concept that we have introduced here. So now let's go back to the equation that we have now that we have a definition of k. That's going to allow me to really simplify the notations. In fact, the notations now, if I substitute omega over v by k, we find that the general solution, at least one of the specific 4 that we discussed. Remember, we had 4 possibilities, plus or minus ikx plus or minus vt. Here we focus on just one. We see that you can now rewrite it as ei omega t minus kx. And this is the general shape that you will see in many courses in physics. And everything comes from the definition that we discussed. So it's useful to look at a quick example here. Imagine that you have 2 waves which have the same amplitude, and one goes to the left and one goes to the right, just as an example. So let's have a look at this wave here. And I'm just summing the two waves. Again, going to the right, going to the left will be plus Vt, going to the right minus Vt, and we decide to add these two. So this is just an example. So in an example, we do whatever we want, right? So long as it's correct. And we say it's the same amplitude. So we can simplify this a little bit by putting minus ikx in front of everything. And we see something that we usually like when we work with exponential. We find the sum of two of them with opposite argument, which is obviously twice the cosine of omega t. So we end up with this particular solution. It's also a good place to remind ourselves that in those vibration, the part of the solution that matters is really the real part. And the real part of that solution is 2a cos kx cos omega t. And when you have a wave going to the left and a wave going to the right, you end up with what's called a standing wave. And what we mean by standing wave really is something very simple, is a wave that has points that do not move. And in fact, if you were to plot this function 2a cos kx cos omega t, you see that there are a number of nodes of this function. And those nodes, because these are the nodes of the cosine, those nodes are points that are never going to move as function of time, and these are called standing wave by that. So that's the definition of standing wave, is a wave where we have points that are not moving at all during the time. So that's really good. Before I wrap up this screencast, I want to discuss the example in details and see how we can apply everything we've learned so far to a specific example.
So these are the two equations that we have. Given the value of A, what are the value of B and C? I'd like to remind you why we can choose A to be a real number. Is because choosing A to be a real is essentially choosing the phase of the coefficient A to be 0, to the complex phase. And this is essentially the same as deciding at what time we start the clock. So it's the reference point of the clock. Now we have to impose two boundary conditions at the boundaries between the two, the piece of strings of different densities. So let me take a minute here to explain to you what the boundary conditions should be. The first boundary condition should be that because the string is continuous, there's no discontinuity in the string, the perturbation has to be continuous as well. Okay, so the fact it is continuous is simply saying that you do not have a big jump in the elongation, in the deformation. So that's written in the continuity of the wave function is simply saying that x equals 0, and I remind you as x equals 0 is at the boundary. That has to be continued. The function has to be continuous. And if I plug that in the solution of psi1 and psi2 that's on the top left of the screen, we find that a plus b is equal to c. Remember, b and c can be complex numbers. The second boundary condition is slightly more subtle, but I'm going to try to explain to you. It is clear that the wave equation involves only second derivative with respect to space, so x, and with respect to time. Now, it's clear that in order to solve such an equation, and for this equation to represent a physical phenomena, those second derivatives must exist everywhere. In other words, they cannot be infinite, or should I say, they can be neither infinite nor singular. And so, for that, saying that they should be well behaved is the same as saying the first derivative has to be continuous. So the first derivative being discontinuous, that's what's written on the top of the second box there, is the same as saying that the second derivative exists. As you know, if you are not able to calculate the derivative of functions coming from the left and coming from the right, then you can't calculate the second derivative. But we know the second derivative must exist since it has to be, we have to be able to find a solution to the wave equation. So now, if we apply this condition into the solution psi1 and psi2, we obtain the condition of minus k1 times a plus k1 times b is equal to minus k2 times c. Now we can put everything together, and using those two equations, we can calculate b and c's as a function of a's. So we see something interesting here. We know that the k's are, of course, real, right? It's just a relation between frequencies and velocity. So b and c's are actually also real in this case, because a was chosen to be real. So there is no dephasing. There's no dephasing. Well, actually, there's definitely no dephasing in c, because c is always positive, same sign as a. So that means that the propagating the transmitted wave, so the wave that continues through the boundaries, has the same phase as the incoming wave. However, b could be either positive or negative. That, in other words, they can be the opposite sign of a and b depending on the value of k1 and k2. So in that case, there is actually a phase difference, but the phase difference is 180 degrees, so it's a minus sign essentially. So we can calculate b and c, and the values are going to depend on that. Now we can also look at the reflection and transmission coefficients. The reflection coefficients will be the amount, the intensity of the reflected wave, so b square, so modulo square, and modulo square of a. And using the equation we just described, we found the reflection coefficient is a function of k1 and k2. But we also know that the total energy is conserved. So the energy of what's transmitted and the energy of what is reflected the sum should be a constant. So that means that we can calculate the transmission coefficient, and the coefficient is going to be 1 minus the reflection, so that the transmission plus the reflection is equal to 1. And that one as well we can calculate using the values of r and so on and so forth that we've calculated before. So one possible mistake that happens sometimes is people think that transmission should be c squared over a squared. It's actually not quite right. The transmission should be k2 over k1 times c squared over a squared. But you see here, using the general solution that we found in the first part of this screencast, and using them to analyze a problem like this one is actually pretty straightforward. I'd like to also attract your attention of one concept that I reminded you about, which are the boundary conditions, both on the deformation psi, but also on its derivative. So I hope you enjoyed this screencast, and be ready for some more coming after this one. Thank you very much.